Okay. Calculate the pH resulting, I don't know what page this is on, 5.4, 58? 51, page 51. No? 50, page 50. So the first thing you want to do with any question like this is you want to look at the volume and concentration, and you also want to, the volumes and the concentrations, and you also want to look at the species that you are dealing with. So what is that thing there? It's a base. What kind of a base? It's a strong base. And what do we have here? We have a strong acid. What happens when we put a strong acid and a strong base together? What happens? Pardon me? They will be 100% dissociated, but even more importantly than that, what do the two do with each other? They react. What do we get as our product? NaCl plus H2O. Okie dokie. So we are going to use a variant on a rice table here, except for it's not going to be initial change final, because this is not an, or sorry, equilibrium, because this is not an equilibrium, because these are both strong. So it is a one-way arrow. So instead of ICE, we're going to do ICF. What do you imagine the F stands for? Final. And we're not going to do concentrations. We are going to do moles. Okay? Okay. So, what should we be calculating? Pardon me? Everything but H2O, yes. And what can we start by calculating? Moles of NaOH, let's do that. Moles of NaOH. I'm going to put a little I down there. What does that stand for? Initial, okay. How do I do that calculation? You want to cancel out the milliliters and liters. Now, question, are you comfortable working in millimoles? Okay. Fine, you guys like writing times 10 to the negative 3 multiple times in a cramped little space. Not my idea of a good time, but okay. 0.0500 liters times 0.150 moles per liter. Yeah. Yeah, but it'll give you the same answer. It doesn't matter, right? And now I have to do this on a calculator because otherwise I'll put my 0 in the wrong place or my decimal in the wrong place. Times 0.15 equals 7.5 times 10 to the minus 3 moles of Na whoops, OH. So that's my initial moles here, 7.5 times 10 to the minus 3 moles of NaOH. What else should I be calculating? Moles of HCl. Okay, so I am going to do my moles of HCl, initial, which is what? 0.50 liters times 0.150 moles per liter. 0.200 moles per liter equals, where did we get to here? 0.05 times 0.2 equals 0.01 moles. So I'm going to go up here and I'm going to write 0.01 moles. Now they're going to react together. Who are you going to run out of first? You're going to run out of NaOH, so the change is going to be minus 7.5 times 10 to the minus 3 moles, yes? And this is going to be minus 7.5 times 10 to the minus 3 moles, because this is 1-to-1, and then this is going to be, it doesn't matter what you end up in the product because we don't really care about it. Do we want to put it in? Do you care? No. Okay. So we're ending up with 0 because that is our limiting reactant. And HCl is our excess reactant. And then we have to do the subtraction, 0.01 minus 7.5 E3 negative equals 2.5 times 10 to the minus 3 moles. And if you've done it in millimoles, you'll see that your numbers look a lot nicer than that. They're just prettier. However, now at this point, I really haven't left enough room for this because I've got like water all over here doing something over there and I don't even need it. But we need to find the concentration of HCl. Yes, because we need to find the pH. And the only thing left we have is the HCl. So our concentration of HCl, maybe I'll just get rid of these here. There we go. That makes it a little bit better. Concentration of HCl is equal to 2.5 times 10 to the minus 3 moles over how many liters? Oh, 0.1000 liters is good because we've added the two volumes together. Okay, so divide by 0.1 equals 0.025 molar, and that is also equal to what? If that's our HCl concentration, it is also our H plus concentration because it dissociates completely 1-to-1. And so now we have, what was it? pH equals negative log of H equals negative log of 0.025, which is log 1.6. And let's check how many sig figs we want to have in this thing. Ooh. So when I did my subtraction, that would be 0, 0. Yeah, that would be again another vote for millimoles here, because then your sig figs would be easier to figure out because your subtraction would look nicer. Just saying, just saying. Okay, so that was times 10 to the negative 3, so that's 0.0100, and then I've got 7.5 times 10 to the negative 3, which is 0.07, no, 0.0750. So now my sig figs are here, which means that when I have the 250, it's only got 2 sig figs. Am I correct? Did you follow that with me? Okay, so 2 sig figs, so it should be 1.60, 2 sig figs there. Is good? So all you really need to do, and you don't need to make the ICF chart, it is not a requirement. You can simply do this as a regular, excess question and say, how much excess acid do I have left? But it is a nice tool that some people like, so I thought I would show it to you. Do you like it? Do you feel ambivalent? Do you not like, how are we feeling about the ICF? Either way, yes. Why isn't the pH just 7? Because I have more acid than I do base. So I've neutralized all the base, but then there's some acid left over, because you can see, although they have the same volume, the concentration of the acid is higher, and so there's leftover at the end. So basically what you're doing is you are finding the excess, right? And so you don't have to use an ICF to do that. Shall we do the other one without the ICF? Just to see? Okay. So let's see. Huh? Millimoles this time? Oh, bless. Excellent. Okay, we can do it in millimoles this time. So my millimoles, oh, and this is a 1-to-1 relationship, so I should write that down. I've got HBr and I've got KOH. And I can even just take a look at these and make a guess as to which one is going to be in excess. Can you guys guess which one will be in excess? Probably KOH, yes, because although the molarity of the HBr is larger, it's not larger by that much compared with how much the volume is larger on the other one. So probably the KOH is going to be in excess. So if you're not ending up with a pH above 7 for your final answer, you know you've done something wrong. Yes? So let's find our millimoles of HBr. And that is 75 milliliters times 0.2 moles per liter. And that gives us 15 millimoles of HBr. Our millimoles of KOH is equal to 225. I guess I should put my 0.0 so I know how many sig figs I'm dealing with there. Milliliters of 0.150 moles per liter. .225 times 0.15 is 33.75 millimoles. Now these react in a 1-to-1 fashion, yes? 1-to-1. So who is used up completely? HBr is used up completely. And when the stoichiometry is 1-to-1, it's super easy to say how much of the HBr, or sorry, of the KOH was reacted. Yes? Yeah, I would think so, yeah. I don't think you need to. You might just say this is your limiting reactant, just to be super clear, if you want to. I'd be tempted to, just because I'm always the person who wants to be super clear, because I always wanted my teachers to know exactly what I was saying. But, you know, I don't know what they're looking for in the AP exam exactly in terms of that. So, millimoles of KOH reacted, how do we know? Well, it's because this is 1-to-1, so it's equal to how much? I want to know how much reacted, not how much is left over. 15, yes. Okay. And so then the millimoles of KOH left over is equal to 33.75 minus 15. And you can just put brackets around that and millimoles on the outside so you don't have to write it twice. And you get 18.75. How do we calculate concentration of KOH? Yep, so 18.75 moles, millimoles. And that's the only trick about doing millimoles, is if you're like me and you forget to write the millimoles, and then all of a sudden you're like, what? Crap! Ah! And then the total volume, 75 plus 225. Oh, look, I can do that in my head. That is 300. Okay, and we get 18.75 divided by 300 is 0.0625 molar. And that is our concentration of KOH, which is also equal to the concentration of OH minus. And just to remind you, we can do it a different way from how we normally love to do it. How would we go about finding hydronium concentration from that? Kw over OH minus. Although I'm with you if you like doing it the other way, because I like doing it the other way, but just to prove we can. Did I do it wrong? Huh? Oh, the question asks for POH. Well, dang. If it asks for POH, then we don't need to do that at all. Not reading the question. Remember? You guys know that one? Read the question 2 times, or if you're feeling more emphatic, okay? Woo! Pretend you didn't see that. It's just a letter. Okay, which I obviously did not do since I went and tried to find the pH. Okay, so pOH is equal to the negative log of 0.0625 and 0.0625 log 1.204, and then that would round to, I believe, up here we had a 75.0 milliliters, so that's 3 sig figs. So I think we are good on the sig fig front. Yes? Okay. Oh, what do you think about this one? There's something a little different here. We have 2 OH minus, yes, for every one. So this is not going to be one-to-one stoichiometry. One of the ways of doing this that is sometimes easiest is just to find the moles of hydrogen and the moles of hydroxide, because then you don't have to worry about the stoichiometry between the barium hydroxide and the hydrogen. You just go, oh, I can just go with that. Do we like that way of doing it? Do you have any idea what I'm talking about? Kind of? Okay, so we could either go through the whole process of saying I have HCl, 2HCl plus BaOH2. I would find my moles of HCl. Actually, I would find moles of product from each to determine the limiting reactant. Yes, do you remember doing that for limiting reactants? If you don't, I will go through that. Would we like me to go through that? Yes? Okay. So we're going to do it that way first, and then I'm going to show you the other way, which is faster. So have some extra paper, because there's not going to be space to do both of them in the space provided. Okay? So let's start by doing the limiting reactant. We have 25 milliliters. I'm recording. Yeah, we have 25 milliliters of 0.0420 molar BaOH2, and we have 125 milliliters of 0.0120 molar HCl. Okay. Now we need a balanced reaction. So we have HCl plus BaOH2 gives water and barium chloride, BaCl2. Is that balanced? No. Now, one thing when you're doing acids and bases, if you want to balance it, you must have the same moles of hydrogen as hydroxide. That's an easy way to balance acids and bases. So what should I do with my HCl so that I have the same number of hydrogens as hydroxides? I'm going to put 2. And if I have 2 hydrogens, that means I'm going to have 2 waters. Yes, because I'll have 2 hydroxides and 2 hydrogens, which is going to make 2 waters. So to find the limiting reactant, find the moles of product produced by each. There's actually another way of finding limiting reactant that might be a little faster in this case. If you know it, you could use it, but this is the way we learned last year, okay? Find the moles of product produced by HCl and by BaOH2. So, which product do you want to find? Does it matter? No, pick one. Which one are we doing? H2O, sure. Just pick one. Okay? So we're going to say moles of H2O from BaOH2 is, let's see, shall we do millimoles? Yeah, okay, millimoles. 25.0 milliliters times, oh no, that's the, yeah, from BaOH2 times 0.0420 moles per liter, and that's moles of BaOH2 per liter times 1 mole, 2 moles of water, 1 mole of BaOH2. You're going to love the other method when I show you because it's so much less work. Okay. So we got that. Whew. And that gives us 25 times 0.042 times 2 equals 2.1. I'm going to plug that again just in case I did it wrong. 25 times 0.042 times 2, 2.1. Okay, 2.10 millimoles of water. So that's how much water we could get from the BaOH2. Millimoles of water from HCl. And HCl, we have 125 milliliters, 125 milliliters times 0.0120 moles of HCl per liter times 2 moles of H2O for every 2 moles of HCl. Did I get that right? Yes, I did. Okay, that's good. Equals 125 times 0.012 equals 1.50 millimoles H2O. Who is the limiting reactant? HCl is our limiting reactant. So we will use up all of the HCl, and we will have some of the BaOH2 left over. Yes? So how are we going to figure out how much BaOH2 is left over? We need to find out how much BaOH2 is used up. So we're going to start with, what are we going to start with there? I'm going to start with my 25 milliliters, and I'm going to start with my 125 milliliters. What am I going to start with? Sorry? If I start with 25 milliliters, I will end up calculating how much BaOH2 I have at the start, because that's the milliliters of BaOH2. I want to start with my limiting reactant, because anytime I'm figuring out how much is used up, I'm going to start with the limiting reactant. So I am starting with, I'm going to use up all of the 125 milliliters of BaOH2. And let's convert that into moles of BaOH2, 0.0420 moles BaOH. Yes. HCl, thank you. What's wrong with me? HCl times 0.0120 moles of HCl per liter. So what we have now is we have the millimoles of HCl, and we want to know how many moles of BaOH2 are reacting with that. So we need to convert moles of HCl into moles of BaOH2. 125 times 0.012 divided by 2 equals 0.0750 millimoles of BaOH2 used up. Oh dear God, and I have to calculate how much there was at the start too, don't I? You guys are gonna love the other method because it's so much faster. Yes? Okay. 125 times 0.012 divided by 2 equals 0.75. There? Better? Yeah. Okay. So how much BaOH2 did we have at the start? Oh, good God. Millimoles of BaOH2 at the start was, we started with 25 milliliters. And we had a concentration of 0.0420 moles. BaOH2 per liter. And we get 25 times 0.042 equals 1.05 millimoles of BaOH2. It was 0.042, wasn't it? Yeah. So that's how much we had at the start. This is how much we used up. So the millimoles of BaOH2 left over is equal to 1.05 minus 0.750. So the amount at the start minus the amount used up. And now you're thinking, oh, now I kind of remember why I had trouble with moles last year. I thought moles were so easy. There's just a lot of work involved, and there's a lot of places you can just make stupid little mistakes, right? There are ways of doing this faster. I don't know if we have time to go over it today, like with actually using a limiting reagent sort of thing without going to H and OH first. But does this seem like a pain in the ass? Okay, but we've gone through a limiting reactant problem, so we've hopefully had a refresher of that. That was really why I went through that process, is so that you could remember how to do a limiting reactant problem. Figure out how much product you make from each one, figure out, how much was used up, figure out how much you had at the start, do the subtraction. Okay, so that was that review there. Now, what if instead we simply said, I'm going to find my moles of H plus and my moles of OH minus instead. And I'm going to look at my net ionic equation, which is H plus OH minus gives H2O. Because if I were to actually write out this equation, right, if I wrote my complete ionic equation for that, it would be 2H plus 2Cl minus gives, or whoops, plus Ba 2 plus 2 OH minus gives 2 H2O plus Ba 2 plus 2 Cl minus. Ooh, that was exhausting, yes? Chlorides cancel, barium cancels, and we are left with 2H plus 2 OH minus gives us 2H2O, which simplifies to H plus OH minus gives us H2O. That is the net ionic equation for every single strong acid, strong base reaction. I don't care what the stoichiometry is between your original components. If you break it down into hydrogen and hydroxide, you have a one-to-one reaction, and then you don't have to diddle around with all that. Who's the limiting reactant? Whichever one has the smaller number of moles is the limiting reactant, and your math becomes so much easier. Does that make sense? Yeah, if you can always get this is the net ionic reaction for all strong acid, strong base, whoa, come on, neutralizations. And limiting reactants are so easy when you have one-to-one stoichiometry, right? So let's do it that way. So let's find our moles of H. Moles or millimoles, what do you want? Yeah. Because they're both strong. Well, HCl is a strong acid, BaOH is a strong base, so they neutralize one another. Will Cl minus take chloride back and become HCl? No. It does, but only to the extent that water does. Because you now have water, like it'll do it like where you have a concentration of 1 times 10 to the minus 7 of each. Does that make sense? Yeah? Okay, cool. So it's not that this doesn't happen, but it's only the normal autoionization of water. You make the water, it's like a precipitation reaction. You make the precipitate. And you don't really care that a solubility equilibrium is set up afterwards if you're dealing with the precipitation. Yes? Similar here, if you're dealing with the neutralization, you don't really care that there's this tiny little bit of autoionization of water afterwards, it's pretty much meaningless, yeah, in the context of the entire thing, because it doesn't affect the pH. It's still going to be 7, right? Okay, so where did we get to? We were over here. So we're going to find moles of, do you want moles or do you want millimoles? Doesn't really matter. Millimoles, okay, so millimoles of H plus. So we're going to use our H plus information here. Oh, I'm trying to draw with a highlighter. That's not good. So we have 125 milliliters times 0.0120 moles of HCl per liter times 1 H plus for every 1 HCl. Now we're going to do the same thing with OH, but we're going to be starting with our 25 milliliters of 0.420 molar BaOH2, and we're going to have to convert it to hydroxide. So we have 25.0 milliliters times 0.0420 moles of barium hydroxide per liter. And now instead of just having 1 mole of hydroxide, we have 2 moles of hydroxide for every 1 mole of BaOH2. And we get 2.1 millimoles of OH minus. And because we're now in a 1-to-1 stoichiometry, we can simply say that 1.5 millimoles of H plus is limiting, which also means that 1.5 millimoles of OH minus is used up. Yes, because it's 1-to-1. So 1.5 millimoles OH minus is used up because there's 1 H plus for every 1 OH minus, which means that the moles, millimoles of OH minus left over is 2.1 millimoles minus 1.5 millimoles is 0.6. Oh, 3 sig figs there, so that's going to put us there, 60 millimoles of OH minus. And now you can just put that hydroxide over your total volume and find your concentration of hydroxide, find your pH, find your pOH, find whatever you need to. Do we like that better? Yeah. Was it worthwhile having seen a limiting reaction problem again? Okay, good. There is another way of doing the limiting reaction problems. Do you want to see it, or should we just keep moving? I feel like we should just keep moving. Yeah? Okay, good. Did you want to try that one on your own, number 4? Try number 4 on your own. Mm. Mm-hmm. Um, you you can like how would you what would you do specifically? How would you show your work? Yes. Mm-hmm. When you say just by using that, how are you going to show your work just by using that? Okay. Yeah. Okay. You can do it that way. Yes. Yes. That was what I was saying. There are other ways of doing limiting reactants that we haven't done. Yeah. Okay. Yeah. Have I goofed up somewhere? Oh. Whoa, yeah, you're right. Holy moly. Okay. Yes, it does seem incorrect. Don't you wish you could like have the class like, you know, look at your answer before you had to submit it? Wouldn't that be nice? Everyone else check. Is my math good? Did you? That's good. I remember actually, I clearly remember being in university, first year university, doing this, and they were doing it in millimoles, and I'm like, what the F is a millimole, and why are we doing millimoles? And now I'm a total millimole convert. Did I do it wrong? Where? Oh, does it ask for POH? What a stupid question is that? POH equals minus. Now, I'll be honest with you, chances of you getting a question with a 2-to-1 ratio are much smaller than the chances of you getting a question with a 1-to-1 ratio. I just felt I needed to put these in here because, you know, otherwise everyone just thinks, oh, it's 1-to-1. Whatever one I have the smaller number of moles of is the one. Yay! Okay. So it is important if you don't have 1-to-1 stoichiometry that you do go to the net ionic equation first. Okay. Whew. Was there anything else in here? Okay. Whoa. Okay. Shall we try something else? Because that was very grindy. I did not like that. There are buffer videos. So if you are unhappy at any point with the lessons that I teach you in person, there are videos that I taught actually this would have been 2 years ago now. Okay. There are videos for Colger. Colger has all his buffer videos, and you know he tends to be less long-winded than I do, so you can be like, oh, 7-minute video, woo, instead of a 32-minute video, okay? So, but his voice is very bland, so yes, there are trade-offs. You can just put me on, you know, 2 times fast, and it's better. You know, you have half the time right there. Okay, so those are your buffer videos, but we're going to actually talk about buffers. And this is on page 55. A buffer solution is one which, and hopefully maybe some of you have heard of this from other courses, maybe in biology or something like that. It resists changes in pH. Yes? And it resists changes in pH when a small amount of strong acid or strong base is added. So, yes. It gets really, I mean, no, you could add a small amount to the other one. It's just that it gets really complicated. So we're not going to give you calculations around it when you're adding a weak one, because then you end up with, like, you know, 3 different equilibria all competing with one another. And we don't want that. Yeah? So it's not that it doesn't work, but it just gets complicated, the math. So we will only be looking at the math with the strong acid and strong base. Okay? The buffer minimizes the change in pH when acid or base is added. So let's just say you have some 1 molar acetic acid. It forms an equilibrium, does it not? Yes? However, if we crank through the math on this thing, we would end up with a very small amount of hydronium and a very small amount of acetate, yes? And 1 minus 0.004 is approximately equal to 1, okay? Chris, could you close the door for us, please? People out there singing and, I don't know, dancing or something. So, will this equilibrium be effective in bringing H3O plus back to close to its original concentration if we add 0.1 moles of NaOH? So if I add NaOH, what will happen to this equilibrium? If I add NaOH to this equilibrium, what will happen? It's going to shift to the right. So will it bring the hydrogen ion concentration back up? If it shifts to the right? Yeah, so if this goes down, but then it shifts to the right, then the hydrogen, it goes down, but it comes back up. Does it get to its original concentration? No, but it does get close. Yes? So the answer then is yes. It shifts right. Okay. How about if we add some HCl? Let's take a look at this. So now I'm adding some HCl. Which way is it going to shift? To the left. Now I want you to think about how much you have here and what's going to happen if it tries to shift to the left. Pretty soon we are going to run out of this guy, yes? So if it tries to shift to the left, we can absorb a tiny, tiny, tiny amount of acid, 0.004 molar, but then we run out of the base. Yes? So the answer is no, because we run out of CH3COO minus as we try to shift right. So we do not have a buffer solution here because we can only, it will only keep the pH fairly constant if I add base, but not if I add acid. Yes? Now what we're going to do though, is before we add any of these things, we're actually going to add something else. We are going to add some sodium acetate. Okay, sodium acetate to the equilibrium mix. Yes? Huh? Left, yes. As we try to shift left, thank you. So now what we have is now we have a concentration of CH3COO-, which is high. Now as we try to shift to the left, what will happen? Will we succeed? Yes, we will. So what you'll end up with is that as we add the sodium acetate just to the acetic acid solution, the CH3COO- goes up. In response to this stress, the equilibrium will shift to the left, causing H plus to do what? Decrease. And CH3COO to increase. Right, because we're shifting to the left. So I added more of this. Oh, yeah. It's all good. It's all good. Okay. So now we have concentrations that are approximately 1 molar, you know, a little bit more here, approximately 1 molar here, and a very low hydrogen ion concentration. But this system will now be able to shift in either direction in response to stress of either hydroxide or hydronium. And that is all a buffer is. You have to have a weak acid, so you have an equilibrium, and you have to have its conjugate base. Okay? You cannot have a buffer solution just with the weak acid. You cannot have it just with the conjugate base. You have to actually physically put both of them in the container together. Okay? So you have to have high concentration of weak acid and also that high concentration of weak base. I feel like we answered this already. Will this be effective at shifting in both directions? So if I add some NaOH, can it shift to the right? Yes. If I add some HCl, so that brings up the hydronium, can it shift to the left? Yes. Is good? Okay. Why does it have to have both? Well, if I didn't have this one, it couldn't shift to the left because there would be no base for the acid to react with. So a buffer needs to be able to either produce extra hydronium or use up extra hydronium. If we only have the acid form, and if this was 0.004 molar, if I start adding H+, this is going to try to shift, but what's going to happen to the CH3COO-? It's going to run out. Yes? Doesn't matter, because you're just trying to keep it constant, okay? Both of them have to be in high concentration, the acid and the base form. So this has to be high, and this one has to be high, and it really doesn't matter what the H3O+ is. We can actually do the math around that to make it whatever we want by choosing the correct acid. Oh yeah, no, the hydronium does the hydronium does not have to be high. No, the concentration of the acid has to be high, the concentration of the base has to be high. The hydronium is the hydronium, it's not the acid or the base. The conjugate base and conjugate acid pair both have to be high. Yes. Okay. Cool. We're at 5 after. Let's make sure that you guys are feeling really good about hydrolysis. So how about you do, oh, I don't know, can I put it online? Okay, good. Then you guys can go and you don't have to listen to me ramble about which question you're doing. All right. Whew. I'm going to go post it today. Yes, yes.
I couldn't find like
No, I've kind of gotten really bad at doing it. Yes.
find on notes, right?
You can find it here, but I should be posting it online, in theory. Yeah.
All right.
Hi. Yes.
Any way that we could get like a refund for the Is any way?
I don't think so.
I heard last year that there was, and they
but
changed it again.
Last year was a bit of a weird situation because of COVID. You can always just not write. I mean, it sucks that you lose the money,
Yeah.
right? But there's nothing to stop you from just saying, no, I don't want to write this thing, because it's a lot.
Well, and you know, I was feeling like I was like, okay,
Yeah.
like I know like I
Yeah.
can do it, but the weekend before, like right before the
Yeah.
exams, like first week of May.
Yeah.
I'm in a
Awesome,
tournament in
doing
Seattle.
a ton of stuff. Yeah.
Yeah. So
Yeah.
and I can study there, but
Yeah,
like
it's just
that's
not
also,
the same. Yeah.
Yeah. So and
Yeah.
that really stressed me out.
Yeah.
Oh, I'm not gonna feel prepared going into it.
No.
But if I can't get the money back for it, I will want to write it. But you know, in the end, I wish I listened to my mom before, because she's like, don't do it. It's so unnecessary. Because she's like, at first I signed up. I'm like, oh, I'm gonna prove it to myself that I can do this. And then I'm like, well, I'm gonna take first year chem and first year bio again next year.
Yeah. Yeah.
It's not like even if I pass it, I'm not gonna.
You're gonna take it anyway.
Yeah, because I want to make sure I'm very
Of
solid on
course,
everything.
of course,
So.
yes. I
And
think
then
that's the smartest thing to do.
Yeah.
Yeah.
I was like, yeah, don't take it. It's so unnecessary.
Yep, should have listened to mommy.
Really
Mommy is,
should've.
your mother is wise.
Really should have.
She's
And
a
then I
wise
heard you
lady.
say it, like, oh, I haven't taken it. And I was like, oh.
You're like, no, I'm gonna take it.
I was feeling a little bit too ambitious.
That's okay. That's okay. Do you know what? That happens to so many people in grade 12 because like things pile up, and it's not just like, you know, I'm not doing it because I'm not ready. It's because I've got 7 other things happening at the same time, right?
I took these at first.
Yeah. You're welcome. You could ask Ms. Riley. She might know. Yeah. That's not yours. Let me find yours.
So, can I check over my work? Yes, Oh, really?
Where have I put yours? It was like a little bit of it. Yeah. Do you want to like close that so it's not like blinding you? Yeah. Okay. Now. Where did I put it? Woo! There we are. Okay, so we have that one. And then Chloe is still doing here.
I can change anything.
Yeah, don't change it. No. Why don't you just not look at this one? I'll just give you the one. Yeah, it'll do. Otherwise, you'll just stress yourself out. Yes. Yes. Okay. So we've got that for you there. So Young, I just have to find yours. Yours is right here. Do you need your bubble sheet as well? Like that? No? Okay. Thank you. Perfect. Ooh, that didn't make you nervous? Okay. That's okay. You don't need to know most of it. Thank you so much. It's okay. It's okay. See, you got one. You got yeah, exactly. You know what? Even if you only got one, that's good. It's better than zero, right? You can't know what you didn't learn, right? Grade 11. Yeah. Don't worry about it for like grade 10. No. No, grade 10, you will learn all of the stuff that we learned again. And then they're going to add on things like instead of just write, we're going to write chemical formulas this year. Next year, you'll write chemical formulas and you'll show the whole reaction. And you'll show like how to balance a chemical reaction. So the amount of stuff equals the amount of stuff. Yeah. So, yeah, it's not too bad. You'll like that part. It's easy. Have a great evening. Oh, right. And I need to stop recording.